twice IZZ for the web will be twice. The width will be 145. No, what do you mean the width is going to be 145? Come on, Eugene, wake up. The width will be 10. The depth will be 300 cube. Okay, 300 cube over 12. Okay. So first set is 300 power 3 times by 10 times 2 divided by 12. It's going to 45 times 10 to the power 6 millimeter to the power 4. Okay, let me do it again. 300 power 3 times 10 times 2 divided by 12. So I've considered left and right. So IZZ for the upper flange. Okay. So because upper and lower below their up, there's one. So this is the section I'm interested now. The one at the top and the one at the bottom. So that's why we put twice. Width is equal to 125. Depth is 10 cube over 12. Then because the centroid of the upper flange is at a different location from the global centroid, we have to do the area and then multiply by 150 minus by 10 divided by 2 and squared. Okay, so this will be equal to 150 minus by 5, 150 minus 5 squared times by 125 times 10 plus by 10 power 3 times by 125. I got this wrong. I should have a big bracket on the outside. Apologize. Okay, let me do it again. 150 minus 10 divided by 2 squared times 125 times 10 equal plus by 125 times 10 power 3 divided by 12 and times 2. So it's 52.583 times 10 to the power 6 millimeter 4. Let me do it again, please. Squared times by 125 times 10 plus by 125 times 10 power 3 divided by 12 times 2. 52.583. 52.583. So 125. The width is 125. Yep, correct. And then the next one, IZZ, lower flange. So it's twice. The width is 125, so the depth is 10 cube over 12 plus by the area. Now is no more 150, okay, minus, so now it's 10 plus 100 plus 10 divided by 2. And then the whole thing is squared. Okay. So this will be equal to 100 plus 10 divided by 2 squared. That's 125 times 10 plus 125 times 10 power 3 divided by 12 times 2 is equal to 27.583 times 10 to the power 6 millimeter 4. Let me do it. Yep. So I total or IZZ will be equal to 45 times 10 to the power 6 plus by 52.583 times 10 to the power 6 plus by 27.583 times 10 to the power 6. Okay, so 45 power 6, but 583 power 6 plus 27.583 power 6 is equal to 125.166 times 10 to the power 6 millimeter 4. Let me do it again. 44 power 6 plus. Yep. Okay. Or it can be equal to 125.166 times 10 to the power minus 6 meter 4. Okay. So once we get here, we can find, right? We can find the Q Z at point A, which our now we know the area of interest. Okay. So we can find QZ at point A. So the width is 125. The depth is 10. The Y bar is 150 minus 10 divided by 2. All right, 150. Yep. Okay. So this will be equal to 125 times 150 minus 5 times by 10 times 125 is equal to 181.25 times 10 to the power 3 millimeter cube, or 181.25 times 10 to the power minus 6 meter cube. So the Q at point A is equal to the shear force is 18 times 10 to the power 3. And then the Q is equal to 181.25 times 10 to the power minus 6 divided by your IZZ is 125.166 times 10 to the power minus 6. Okay. So 18 power 3 times 181.25 power minus 6 divided by 125.166 power minus 6 is equal to 26. I do apologize. I make a mistake. Okay. So there's one Q over here. There's the other Q over here. You have to divide by 2. This is because of 2Q. Okay. Box beam analysis. Right? If it's white flange, you don't need to divide by 2. Okay. So 18 power 3 times 181.25 power minus 6 divided by 125.166 divided by minus 6 divided by 2 is equal to 13.03 times 10 to the power 3 Newton per meter. Why Newton per meter? Because the formula for shear flow is VQ over I. So if you look at units, Newton meter cube over meter 4, you cancel this, that's why it's Newton per meter. Okay. So we already know the area, so now we're going to do the first moment of area at point B. Okay, so QZ at point B now. Okay. So once you know what area to take, it is so easy now, right? So 125 multiplied by 10, so that will be 100 plus by 10 divided by 2. Okay. So this will be equal to 125 times 125 times 10 times the 100 plus 5 is equal to 131.25, right? Times 10 to the power 3. Okay, and then this is millimeter cube, or 131.25 times 10 to the power minus 6 meter cube. So Q over here at point B now. V is the same. First moment of area change is 131 now. and then divide by I is the same, and then Q is left and right is 2. Okay, so 18 power 3 times 25 power minus 60 power 125.166 power minus 6 divided by 2. So it's 9.437 times 10 to the power 3 Newton per meter. Okay. The most important thing is to find the what do you call it? I'm lost of words now. To find the once you know the first moment of area, things will be easier. Okay, things will be easier. Right. Now the next one I'm going to do. In the next one I'm going to do, we have to be like really careful. Okay, the next one. Now I will not find first moment of area, our second moment of area. I realize that that's a bit of waste of time. I think now all of you could find second moment of area. Sorry, someone's on the chat. Okay, it's okay. Okay, now let's look at. So we have done like 2 different examples already. Okay. Then we do another one. Okay, example number 3. Now example number 3 is I'm going to hold on. So example number 3. Okay. Good. Gone missing. Okay, the beam is subjected to a shear force of 5, so very similar, and determine the shear flow at point A and point B. Okay. So now we know that. So I'll write. Okay, so this is our transformation. Right. So this is Y, X, and Z. Then I'll write down that our IZZ. Okay. I'm going to focus on the first moment of area rather than second. Okay. So our IZZ is equal to 145. Because I believe all of you know how to find second moment of area really well now. It's the first moment of area that is a killer. Okay. And Y bar, the global centroid, okay, Y bar is equal to 3.70946 inches from the top. Okay. So now we have to again sketch. Okay. Now again we have to sketch the shear flow. Okay. So now I'm going to sketch the beam first. Hey, wrong function. So this is the beam. And then you got another piece down here. Okay, this time I'm not doing it to scale, okay? And then we have a horizontal one down here. A very interesting example. Okay. So now if we were to draw the terminal, or before we draw the terminal, we apply the rule that the major web control the direction of the shear flow. So it goes down here. Right? And then we know that this is a more or less a box beam sort of analysis. Okay, so if I were to sketch our centroid, so for example, this is our centroid. All right. And then we have a terminal down here. Right. So we'll do this. Right. So you have Q on one side, so it's a box beam. And then over here below the centroid is coming to here. Right. So that is our terminal. And these are also our terminal. Okay. So you have T1, T2, T3, and T1, and T4. So we are asked to find point A. So the location of point A is over here. And the location of point B